So we continue our morning session with the great pleasure to introduce Bill Goldman from Maryland, who's going to tell us about
classification of locally homogeneous geometric structures. But I'm also at Hyman's Laufer Institute, so I should say that for another 2 weeks.
Oh, I see.
Anyway, as the next to last speaker, I would like to thank the organizers and the staff for a really nice conference. So please join me. Congratulations. I'm very excited getting here and seeing the energy and enthusiasm. I'm also very grateful, personal level, for the invitation to speak here. It's a great honor, and I think it'll be clear in my talk the influence of Donald Spencer on the subject. So I'm interested in the classification of what I'll call locally homogeneous geometric structures. And these are going to be defined by a pseudogroup, namely ones that arise from a geometry. So this is a way of relating geometry and topology via group theory, via notions of symmetry. And nowadays, I'm going to take a point of view developed in the late 19th century by Sophus Lee and Felix Klein, that a classical geometry such as Euclidean geometry, projective geometry, conformal geometry will be defined by a homogeneous space. So according to Klein's Erlangen program, the geometry is the study of things on X that are invariant under G, transfer group. Okay, so this is a homogeneous space, and it defines a pseudogroup of where the objects are going to be open sets in X, and the morphisms will be transformations between the open sets, which are locally in G. So in other words, the open set might not be connected, but on each connected component, there's a single element of G that defines the transformation. So for example, the Euclidean structure modeled on Euclidean geometry, X would be Euclidean space, and G is its group of isometries. Okay, I think I'll also describe affine geometry, where X is now affine space, and I'll denote that differently. Context, because we identify, again, using ideas of symmetry, Euclidean space or affine space with a vector space of translations. So this is a torsor for a vector space Rn. G, it's affine group. These are isometries are transformations of the form X goes to AX plus B, where A is orthogonal. Affine transformations are more general and arbitrary transformation. And so we all know the properties of Euclidean geometry that are relevant: distance, angle, volume, and area. Affine transformations, the only notion is that of parallels. Two objects are parallel if they differ by translation. Similarly, you have projective space and other Riemannian manifolds. this is a very rich class of things to study. And I'm interested in fixing a topology and asking, when can we take this topological space and give it a coordinate atlas where the charts map into X and the coordinate changes are locally in G. That's what I'll call a GX structure. And I'll usually use sigma to denote just the underlying topology and the GX manifold. So these are going to be related by some sort of weak map where we go from the topology to the geometry. And this map will be, say, a homeomorphism. Now, I might mention that although I'm maybe start with just a topological surface for sigma, these structures are very special. Namely, following Hilbert's fifth problem, every locally Euclidean topological group is really a B group, and every GX manifold will have an underlying real analytic structure. And I'm not sure whether I can say, but most topological manifolds aren't even PL or smooth, which is greater than 5. So these are extremely special manifolds, just like Lie groups are very special topological groups. So, however, my introduction to the subject was in the late 70s through Bill Thurston, and he cast his geometrization conjecture picture in terms of GX structures, where X is a homogeneous Riemannian map, and it could reduce to 8 different model spaces, and conjectured that every 3 manifold be canonically decomposed into geometric pieces of 8 different geometries, and then this was later proved by Pearl, which makes it all more remarkable since these GX manifolds are extremely special. Analytic structures. I think the beginning, the structures I'm going to be considering are more general than the ones that Thurston considered, namely because I'm not going to assume that X is Riemannian. So affine space, for example, has no natural affinely invariant Riemannian metric, and that leads to many more fascinating phenomena than local homogeneous phenomena. I think it's fair to say that the subject began in a paper by Charles Ehresmann around 1936, I believe, where he essentially formulated the question, given a topology sigma, does it admit one of these locally homogeneous structures? And a good example is to classify all the Euclidean structures, and the topology of a sphere is incompatible with the Euclidean geometry. There are lots of, this is when people ask, non-mathematicians ask me what I do. I give this example because this means that there's no metrically accurate world atlas sphere. And the topology of the sphere is incompatible with Euclidean geometry. A Euclidean structure in this sense is easily seen to be the same as a flat Riemannian metric. And that's, and there are many ways of seeing this. The two-sphere has no defined Riemann metric. Gauss-Bonnet theorem is one way, but in some sense even easier, that because of the structure of the coordinate charts, we can get a development pattern. So this is the development structure, which I think really goes back to Elie Cartan. And in this case, you imagine taking a coordinate patch, mapping it into the model space, and then analytically continuing over and overlapping. And so here we're using the fact that the pseudo group comes from a transformation group that's acting strongly effectively, that if you have two transformations that agree on a non-empty set of that. And one can continue, analytically continue the sequence of coordinate charts over the whole manifold. You might have run into a problem when you come back to a region where it's already defined, and this is a problem. You can't define this on the set, but it becomes a map defined on the universal covering space. It's a multi-valued function, classical terminology. And this is equivariant with respect to group of deck transformations. And any deck transformation, the universal cover, is represented by a transformation. Tone transformation. Now, if this chain of open sets is contractible, then it's not hard to see using strong effectiveness that this holonomic transformation is true. But if you just look at make the simplest examples, take R mod Z as quotient as a Euclidean circle, you see that you do get holonomic, which comes from the identification on the name by a translation. So in the case of a GX manifold like M, it has no Euclidean structure for the following reason. Its fundamental group is finite, so its universal covering is compact. Developing map maps it into X, which is non. And the developing map is locally the coordinate chart, so it's an open map. So the image is open. On the other hand, M tilde is compact and X is Hausdorff. So this is X is also assumed to be connected. So that means that the image is open and closed, and it has to be everything. M tilde is compact and X is not. So that's the computation. And then, so this is one more thing. But on the other hand, the topology, the M torus has many structures, I'd like to say. But before doing that, let me raise a question about this pseudo groups. Why doesn't this prove that P1 has no complex structure? Well, the pseudo group of local body holomorphisms certainly has analytic continuation. And so you might think that this procedure works there, but it doesn't. The problem is that the attaching maps for a holomorphic atlas on Riemann surface are not assumed to be globally defined. What's extremely important here is that the transformations are locally in G, where G is a group of transformations to find out all events. So when you're building this picture of the structure, you sort of dragging X along with it with each one. So P1 does have a complex structure. So, so the next simple topology is the torus, and I'll say a lot about that today. And this has lots of Euclidean structures. Two structures. Yeah. So these are all flat. The manifolds are all flat tori. So they're identified as Euclidean space modulo a lattice of translations. And we can classify them. The natural space to classify them is a biquotient, where we take GLNR quotient, the orthogonal group on one side, and on the other side, GLNZ. So this is a nice locally symmetric orbifold. Maybe the volume of M is a natural invariant, which we can innocuously normalize to V1 if you get more familiar space. And so this is the natural moduli space of flat tori. And so two GX manifolds will be isomorphic if there's they have an underlying smooth structure, so it's convenient for category of diffeomorphisms. If there's a diffeomorphism that's locally in G, lies in C. Okay, and this is the space of parametrizing isomorphism. So it's a very nice space. It's not a manifold, but if we think of this homogeneous space, we can think of this as the space of equivalence classes of marked structures. And by a marking is an extra piece of information that's kind of essential in this. That's going to be the mapping from the fixed loose topology into the geometry. And when I say loose, I mean this is, say, a homeomorphism and two marked structures will be defined to be equivalent if this diagram commutes up to isotope. So it's a fairly weak structure in the low dimensions I'm concentrating in. This corresponds to an isomorphism of fundamental groups. As you can see, the fundamental group is playing an important role in all of this. But the labeling of the fundamental group. So what's a marked flat torus? A marked flat torus corresponds to choosing a marked lattice. That's just a basis of Rn. Namely, the lattice itself is just the group generated by the basis, but we're fixing the basis, and then arranging that basis as the columns of a matrix, we get an element of GLNR. The equivalence relation is extremely important. Here it's by isometry, so we can reduce to quotient of ON. And we have this space here, which I'll call the deformation space. And then GLNZ identifies with the change of marking, which you can check, it just corresponds to a homeomorphism of sigma defined up to isotopy. So this I'll call the mapping class group sigma. Now, this space here is a manifold with lots of fascinating geometry as a symmetric space, and the mapping class group acts properly discretely on this space here. And the quotient if you're a function theorist, this is good news because you've got lots of interesting things you can do on the quotient. But this is not really the general case, because the dynamics of the mapping class group can be quite complicated in general. But you might say that the classification problem has been solved by defining this moduli space. Now, there's an analogous classification for Riemann surfaces, and as I just mentioned, the complex manifolds are not GX manifolds, suitably quite different, but the space of marked Riemann surfaces the sigma goes to now M is a Riemann surface. That the space of equivalence classes, that's the type number space. Sigma. Once again, it's a very nice manifold with lots of interesting geometry on it, and changing the marking corresponds to an action of the that acts properly and discretely the mapping class group on the type number space Q sigma, and the quotient is really how it all started. That's the Riemann moduli space. So once again, this is a set where if you're a function theorist, this is good news. But if you're a dynamicist, it's not very interesting because the action is proper. There's no, it's not chaotic and very orderly. Now to get something more interesting, we'll look at complete affine structures. So here sigma is the two torus again. Mapping class group. The mapping class group is GL2Z. And I'm going to look at complete affine structures. Now, an affine structure is the same as a an affine structure is the same as a flat torsion-free affine connection. And even on a compact manifold, such connections are not geodesically complete. Geodesic completeness means that the developing map, the affine space, is a bijection. I don't think I have really time to go into too many of the good examples, but they're abundant and quite fascinating. And these were first investigated by Kuiper around 1950, who classified them. And later, Oliver Bowes, or 2000, I think, showed that this space is homeomorphic to the plane. And the proof, Bowes's proof, well, say something about this. The equivalence relation is very important. So what's an example of a complete affine structure on the two torus? Well, Euclidean structures is an example. However, they're all equivalent because any two bases are equivalent by a linear transformation. So this beautiful moduli space here gets collapsed down to a single point. So you kind of lose a lot of geometry. One way of understanding Kuiper's construction is as follows. You can take the simplest diffeomorphism of the plane, in some sense it's not affine, make it polynomial of degree 2, and then conjugate a group of translations by this map. If lambda is a lattice of translations, then you just look at F lambda F inverse, and that's affine, and not a group of translations. I'll leave the calculation for you to say that much time. It's quite simple. What happens is when you write this out, which is not so hard, the F and the F inverse, the quadratic terms cancel out, and what you're left with is the cross term, which is the linear part of the transformation. And so Bauss classified this in 2000, but the Euclidean ones were a special case. They arise as limits. The general picture of the tessellation you get will be by parallel families of parallel parabolas. Okay, so I was lecturing on this a couple of years ago at the Institute for Advanced Study, Pierre Levine in the audience. And the next day, I got this letter in my mailbox telling me that I was raising the question, is there an actual smooth structure on this deformation space R2? And the origin, the one thing that's notable is the origin is very special. It would correspond. There's one special point corresponding to the Euclideans, which are all limits that in parameter epsilon. Let epsilon go to 0, they're all equivalent. And so Deline told me that what I'm probably looking at is a twisted cubic cone. And so we talked about that quite a bit and found several proofs of this. So a twisted cubic cone is the image of the Veronese embedding from R2 into R4, which is the third symmetric power of R2. And the mapping class group is GL2Z, sitting inside GL2R, and then there's an induced action. So that's the action of the mapping. Now, that preserves the origin at the singular point. This, in retrospect, isn't that hard to prove. What you do is you write down the Christoffel symbols for the splash torsion for each affine connection. It has to preserve area. So by affine, then compute this exactly the equations for that. But what I want to say is that this is a very chaotic action. What's the analog of the Riemann modulus? What's the analog? And it agrees with the same moduli space of elliptic curves in genus 1. But what is the quotient of R2 by linear action of GL2? Well, it has a fixed point with the origin. It has lots of discrete orbits, namely, look at rational vectors whose fixed denominator. On the other hand, it preserves area, Euclidean area, which is infinite. It's an ergodic action by a very general criteria, homogeneous dynamics due to Calvin-Moore. And so it's really chaotic. Being ergodic implies that almost every order is dense. But So function theorists might not be happy because there are not too many functions on R2 invariant over GL2Z, but a dynamicist is quite happy in the sense that this is interesting, chaotic. And I guess I would say that this is probably what you'd expect for the classification. And so I would propose that the solution of the classification problems isn't a nice moduli space such as this, but rather the group action, the dynamic system of the mapping class group acting on the. So this isn't the first time that
You mean like and also maps
yeah.
and things like that, no?
Sure.
Okay.
Right. You have like hyperbolic linear maps. This isn't the first time it appeared. He explained to me what it was that I was trying to do. So we can try to find the analog of the type Miller space, deformation space. So-called the deformation space of marked GX structures on sigma. So this would be the space of marked structures to its equivalence relation. And then from that, we get a polynomial map, which takes a structure into its polynomial representation. So that's a homomorphism of pi, fundamental group of sigma. Yeah. And that goes into hom pi G. Now, in defining the developing map, we had to choose a base point, like maybe a base germ, and then analytically continue that to get the homomorphism. So if we relax the dependence on the base point, this is only defined up to composition with the inner automorphisms of G. So we have a space to find, and let's see, in the case that I want to take, G will be a, say, real algebraic Lie group, pi will be a finitely generated group, and there's a natural classical topology on hom pi G is a real algebraic set. And this action by conjugation will be a nice algebraic action. That doesn't mean that the quotient in the usual sense is very nice. In fact, it's very pathological. So pretty much, even despite trying to take quotients by chaotic actions, any kind of pathology, Murphy's law applies here. So even in dimension one, these spaces are not Hausdorff. This is a fascinating object. In many cases, this map is embedded. And it's a general theorem or paradigm or principle due to Thurston, 1970s, that this map tries to be a local homeomorphism. So we want to give this just the quotient of ordinary sense. So I want to say something about the singularities of this space. So hom pi G is a real algebraic set. It's not a manifold. Let me very briefly say something about the case, my favorite case. This is what X is the complex projective line, and G is its group of automorphisms. Then this deformation space, well, CP1 of sigma, complex projective structures. Sigma, and that maps into what is sometimes called the character variety, hom pi PS2C, modulo inner automorphisms. A lot's known about this map. I should maybe mention first that these are marked structures. So the change of marking corresponds to an action of the magnet class group. And these are homeomorphisms of sigma. They don't necessarily preserve the base point, but they do preserve the base point up to inner automorphisms. So there's a homomorphism from this into this outer automorphism group of pi. So the full automorphism group by the normal subgroup inner automorphisms. And in many cases, if sigma's closed surface of closed hyperbolic surface, Nielsen proved that this is an isomorphism. And this map is equivariant. So this naturally leads to understanding the purely algebraic problem of how do the automorphisms of pi act on the space of representations. And now I'd like to talk about some work in deformation theory and bring in some of the ideas that were developed by Donald Spencer. As I mentioned, this space has lots of singularities on pi g. So what is this Zariski tangent space? Let's take a representation rho. And I want to think of taking a one parameter family, just a curve of representations. So that means that it satisfies this equation for all t. So x and y are elements of pi. So the tangent space will be obtained by linearizing this equation. So what do we get? The tangent space is easily seen to be the space of Eilenberg plane, one cokines pi with coefficients in the pi module given by the Lie algebra of G, twisted by the adjoint representation of rho. So rho goes from G, rho goes from pi to G to the automorphisms of Lie algebra. Okay, so how do we see that? This is pretty straightforward. We want to say rho sub t of x. Well, we want to differentiate it. So when we differentiate it at t equals 0, we're at rho of x. So let's left multiplied by rho inverse, rho of x inverse. That's now close to the identity. So that's in the neighborhood of the identity. It's in the image of the exponential map. So I'm being pretty cavalier about all of this. Forgive me. And so we can write this out as a power series. I'll take u1 of x plus t squared, 2 of x plus t cubed, 3 of x plus higher stuff. And now apply this equation. So the equation for u1 is that it's a cocycle. So just you have u1 minus u1 of xy plus add rho of x u1 of y equals 0. And that's the condition for being a cocycle, homomorphism or a cocycle. What about the two-jet? What happens there? Well, then so u1 is a one cochain pi with coefficients in this local coefficient system. In fact, all these things are. And u1 co-boundary with u1. Now the second term involves solving it to next term. And you get a term that comes from the bracket. Now, V1 of X, bracket with add row of X, mu Y. And so this is the natural cut product or lead product on the cocycles. So we have cocycles, pair them together, you get two cocycle, but use the lead bracket as a coefficient pair. D2. Let's take the cohomology last. Because after all, we want to be able to solve this. You want this to be 0 in cohomology. So this is the natural quadratic form that represents the 2 structure, as we heard earlier. Okay, and then the next term, so this is the co-boundary of U2, apply on to XY. Then we have something similar for the co-boundary of U3. And now, to see identification here, we use natural identification using the Baker-Campbell-Hausdorff formula G, and that's a power series. If you look at higher terms in that, you get 2 higher order, which look a lot like, this is a cut product, and these higher order terms look like secondary operations and the massive. So I started working on this with John Milson, and we were looking at this, and it seemed like I knew a little bit about Massey products, paper that Lee Griffiths, Morgan, and Sullivan wrote on the rational homotopy type of Taylor manifolds, and it seemed like that might be related because now we have higher order one of the main results is the Massey products vanish once you know the primary operations. And so using these ideas, we showed that the tangent cone to pi g. Now, already this is quite interesting when G is a compact group. In general, it's quite general if you take a reductive representation into a reductive. So by a reductive representation, what I mean what is images, zero closure is reductive. But the tangent cone, so this is not Nelson, 1980s. Tangent cone on pi g is defined by quadratic form. So I was excited by this result the first time using structured Taylor manifolds. And the way that we were proving this was the principle of 2 types. Griffiths, Morgan, Sullivan used in the proof of formality. Now, in particular, using the Green's function, we were able to construct a map from Q inverse of 0. Well, actually, we didn't. We were really working in the Durand version. So, Carlos would describe this. This would be the Betty version, and then we want to work in the Durand version where we look at flat connections for one forms on M with coefficients in the local system. G in this would be is now H2 of M with coefficients in the same local coefficient. So just do this in the Durand theory. Prove that the tangent cone was defined by Q. And so using the Green's function, we found a map, at least from the neighborhood of Oregon, into on pi g. Kind of an exponential. So we were interested in whether we actually know that this map, the analytic germ, is actually 2 inverse of 0. And it seemed likely, but we didn't really know what we were talking about at the time. But John gave our paper to Ahmad Nouri, who then shared it with Pierre Deline, and then we got another. I got or John received this 6-page letter from Deline telling us what we were trying to do, and sort of outlined. We sort of started in the middle of the argument, and so we had just arrived at the University of Maryland together, and we spent the next 2 years going through and understanding this 6-page letter. So we had good resources to talk to, because John has just come from UCLA, where he was talking to Mark Green and David Giesecker, and I just come from MIT, where I was talking to Michael Art. Remember, Mike said, "Oh, it's easy, just add nilpotents." I didn't know what that means. He said, "Try it, you'll like it." So after 2 years of working on this project, John and I were able to prove that the analytic germ of pi g at rho is equivalent to u inverse of 0, this quadratic cone. And never really appreciated the utility of thinking in terms of schemes, sort of universal viewpoint. Learned from this project. It's only one of the most enjoyable mathematical projects. We twice a week at a cafe, work through different parts of the letter. Anyway, so that's an example of the singularity of the space of representations. I knew for a long time that the mapping class group acts rather can be very complicated. The mapping class group has a natural homomorphism into the symplectic group, given by the action of a homomorphism on homology, and the kernel is called the Torelli group. And it's quite a fascinating group. Typically, a complicated element would be something that's given by product of Dane twists around curves that separate. So, or if you have a subsurface bounded by looking at the Dane twist in one direction around one. So it's already quite a complicated group, and it does act in a highly non-trivial way on the space of homomorphisms. So something started bothering me. Let me take the case just when G is, say, doesn't matter, say, a compact group, let's say SP2. And let's take rho to be the trivial representation. Now, in that case, the cohomology is cohomology is an ordinary cohomology, so we have H1 of sigma with coefficients Lie algebra. But since it's a trivial coefficient system, this is just a tensor product of the symplectic vector space with the coefficient vector space. Okay. And the action is just a cut, and the quadratic cone is defined by this cut product on the cohomology. So in particular, the Torelli group acts trivially. Now, we know that the analytic germ at the trivial representation is defined by this vector value quadratic form, and it's actually trivial there. So in particular, in its analytics, so analytic continues, it's not hard to see that in this case, the space of representations is connected. So that means that the Torelli group has that trivial, which doesn't. So where's the fallacy? A long time to realize that. The analytic germ is equivalent, but the equivalence is given by this exponential, which involves choosing a Green's function to be able to form the power series. And that is not invariant. And so I'll raise a question which is pretty speculative, but I think it's very suggestive and interesting, is to identify the Teichmüller space of sigma with the exponential maps, the realizations of the quadratic cone inside the space of representations. So are there other ways of doing this besides choosing a conformal structure using this very natural construction? It's very much in the spirit of Goldman. So maybe I'll stop here since it's 11:50. I have a few more things I'd like to say, but I'll take both questions. So thank you very much.
Thank you.